So this problem says that we have a uniform surface charge density of sigma distributed throughout some infinitely large sheet of charge. We'll just assume that's positive charge. And we need to find the electric field everywhere in relationship to that charge. Okay, so let me just draw the charge. So it looks kind of like my drawing from the line of charge, but remember this is a sheet of charge, and so it extends in the out of the paper and into the paper. Okay. So like before, we could use call. Remember, E is just integral of dq. Excuse me. Take that back. E is the integral of dE, which is the integral of k dq over r squared. We could do that, but again, we're talking about a complicated thing where we have to integrate up and down and into and out of the page. So it'd be an iterated integral, a two-dimensional integral. Let's just use Gauss's law. So Gauss's law says that, maybe I'll start down here. The flux through a Gaussian surface is equal to charge enclosed over epsilon naught. So we need to draw ourselves a Gaussian surface. Now this is where things get a little bit weird, because we say we always want to match the symmetry of a charge. But this, really, we only have to match the symmetry for any surface where the flux does not equal 0. I'll show you what I'm talking about. And there's a picture on the PowerPoint slide here that shows a little more 3D representation. I'm going to draw a Gaussian surface that is a cylinder, a hollow cylinder of some radius r at some distance, or you know what I'm going to do? I'm going to call it some radius a, and it extends to some distance r away from the sheet, and let's say it also extends backward some distance r. So why is that? Well, I could have used a prism, a rectangular prism. Maybe we'll try that at the end of this problem and show that we get the same answer. But I'm using a cylinder just because it has fewer surfaces to deal with. It has one surface here and two surfaces there. Oh, it also has 3 down here. So the electric field, just like with the line of charge, is going to point radially outward from the sheet, but unlike the line of charge, the electric field isn't going to be rotated around the line. This is a sheet, so it's just going to extend always in the left or right direction, whether you go into or out of the page. And that's, again, because if, for any component of the electric field that points at an angle like that, there's another differential charge element right next to that one that points in the opposite direction, canceling it out. The only thing that survives is the electric field pointing straight away from the sheet. So we have 3 surfaces. This surface 1 is defined by differential area element. Let's call it dA1 like that, which is perpendicular to the electric field. It's perpendicular up here, and on the front side it's going to point straight out of the page, again perpendicular to that. So the total flux equals the flux from 1 plus the flux from 2 plus the flux from 3, but the flux from 1 equals 0. What about the flux from 2 and 3? Well, over here, the differential area element points that way, dA2, and here it points that way, dA3. So you notice in each situation, the differential area element points, that vector points in the same direction as the electric field, whether it's this way or that way. So they're both positive flux because they both have an angle of 0 between those two vectors. So 2 phi 2 equals phi 3, so the total flux is just 2 times the flux through surface 2. So that is equal to 2 times the surface integral of E dot dA. Oh, not AD, dA. dA2 if you wish. And finishing out Gauss's law, that equals the charge enclosed over epsilon naught. Well, we already said that E is in the same direction as dA2, so this is 2 times E A cosine A2 theta EA2, and we said this angle theta is always 0, so this term equals 1, so it equals 2 times the area integral of E A, sorry, this should be dA. But we also know that E, what does A depend on? Well, the area of the circle is just pi r squared, where r is the distance from the sheet to that surface. Well, all along that surface at distance r, the electric field is the same, so we can pull that out of the integral, integrate, and we just get 2EA2. And that equals charge enclosed over epsilon naught. So what is A2? Well, we just mentioned that, so that's 2E times pi r squared, Q enclosed over epsilon naught. What is charge enclosed? Well, it's going to be, remember this is like, we think of this as an infinitesimally thin sheet because it's a surface charge density. So what is covered by this surface, which is the projection of that surface onto that? Because remember, this is a rectangular, or excuse me, a cylindrical hollow thing. So the charge enclosed is just the charge enclosed by this area, pi r squared, right? So Q enclosed is equal to the surface charge density times the area of 2. So it equals sigma times pi r squared. So going back over here, 2e times pi r squared equals sigma pi r squared over epsilon naught, or E equals sigma over 2 epsilon naught. These two guys cancel. So that is amazing. Why? Because it says no matter where you are, it does not depend on R. No matter where you are, if you're over here or if you're way out here, the electric field is the same. That is not very intuitive, but it's true. Let's look at another situation. What if this were, let's say this is our line of charge, and we were to put a cube around it, which you could do. We mentioned doing this earlier. So I hope you believe me, like we did before. This surface has 0 flux because the area points outward, but the electric field points this way. This has no flux. The one in the back has no flux, and this has no flux. This surface is the only one that experiences the electric flux going through it. So, and the electric field is constant right there. So I can say, oh, I just realized I used R twice. I used R for this and the radius of this circle. I tried to keep that as A, so maybe I'll do that. It doesn't matter, it cancels out. Okay, anyways, back to our cube. E times A equals, and remember that the surface back here, if this extends past the line of charge, it's going to experience flux too. So this would be 2EA, because the flux from here equals the flux from there, where this is 2E length times width area of a cube. So 2ELW equals, again, charge enclosed over epsilon naught. 2ELW equals charge enclosed, which is the surface charge density times the surface itself, length times width, over epsilon naught. What do you know? Length times width cancels. E equals sigma over 2 epsilon naught. So it doesn't matter if you use a cylindrical surface or a cubical surface, whatever, you get the same answer. So what's some applications of this? Well, if you had a capacitor, right? And we consider the capacitor to be infinitely charged, well, we know the electric field set up by this plate is sigma over 2 epsilon naught. But because this is negatively charged and this is positively charged, the electric field points from one side to the other. They both contribute. This electric field consists of the field from this guy and the field from this guy. So basically, the electric field here is going to equal 2 times sigma over 2 epsilon naught, or the electric field is just sigma over epsilon naught. And that is the electric field of a parallel plate capacitor. What if you put an electron in here? Or a proton. Let's put a proton in there. So a proton is going to feel the force from this field, and the force is just Q times E, which is just positive elemental charge, the charge of an electron, but positive, times the electric field, so the force is just E times sigma over epsilon naught. And that equals mass times acceleration. So you could say the acceleration of a proton put into a parallel plate capacitor is E over m sigma over epsilon naught. If you want to find, that's the acceleration of a proton. If you want to find the acceleration of an electron, it would just be negative E over m sigma over epsilon naught, where that would be I hat, if you wish. Let's make that a vector. And so this would be I hat 2. So this would be in the positive direction, the electron would go in the other direction. Because keep in mind, a positive particle always feels a force in the direction of the electric field. A negatively charged particle, like an electron, feels a force in the opposite direction of the electric field. So you could take this and you could dump it into kinematics and you could find velocity or whatever, or you could look at work energy balance, or think the total work on something is work equal to the change in kinetic energy. The definition of work is force times displacement times the angle, Fs, where now the force is just Q times the electric field, and it's in the same direction. If the particle just moves from one side to the other, then this would all equal 1. So equals cosine of theta. So this could be, if we're talking about a proton, E sigma over epsilon naught. Oh, I'm sorry, I forgot the distance there. Times the displacement equals 1/2 m v final squared minus v initial squared. If it starts from rest, you could find the final velocity just like that. Of course, you would have to have the plate separation, S. That would have to be the distance over which the electric field is applying that force. Okay, so lots of different stuff you could do with something like this. All applications, all starting with Gauss's law.